Hi students, welcome back. Today we are going to look at another problem on LeetCode called the clone graph. Let's look at the problem statement first. The problem statement says we are given a reference of a node in a connected undirected graph. So the given graph for us is connected and undirected. So we are given such a graph and we have to return the deep copy or a clone of a graph, which means we have to recreate the graph and return the new graph. So each node, so we are given some format on how the node looks like. So each node has a value and list of neighbors in it. Okay. So there is also some description on how the test case format is. So for simplicity, what they are saying is uh, they take the input of the graph as an adjacency list and each node will point to its, so the adjacency list is indexed by the nodes index. For example, the first node will be at value 1 and so on. Okay. We will understand this through an example. So this is the example given to us. So first let's understand the input graph. So the input is in the form of an adjacency list. What we were told is this is indexed on the node numbers. That means the first one is for the first list, the second one is for the second list, third one, this is the third list, this is the fourth one. Okay. So given such a graph, that means we have four nodes in this graph, which would be 1, 2, 3, and 4. So each list represents its neighbor. So for 1, what are the neighbors? 2 and 4. So this is an undirected graph, so it's just a connection. So 1 is connected to 2 and 4. For 2, it's 1 and 3. 2 and 1 are already connected, so we have to connect 3. For 3, it is 2 and 4. For 3, it is 2 and 4. For 4, it is 1 and 3. So this is the graph that is given to us. So we have to create or clone this graph and return the new graph. Okay. Let's look at another example. In this example, there is a list, but it is empty. So the uh, like the given test case format, this corresponds to one node, which means there is only one node in the graph, and this list is empty, which is why it doesn't have any neighbors. So the new graph will also have just one node. Okay. Now let's look at the third example. Here there are no lists itself. That means there are no nodes in the graph. Okay. That means there is nothing, or you can just say node is null. In this case, we will just return null. Okay. So these are the three given inputs. Now let's take example 1 and see how we can solve this problem. Okay. Let's say the given graph is 1, 2, 3, and 4. So to create a graph, it is clear that we have to traverse the graph. Okay. So since it is a connected graph from the given node, we will be able to traverse the all the nodes of the graph. So to traverse the graph, we can use either DFS or BFS. Okay. Both of them works in this case. We just need a way to traverse the graph. So we will be using BFS, but you can try the same thing with DFS as well. Okay. So to traverse a graph, let's say we are starting here. Okay. So usually what we do is we keep track of, we take a queue and keep track of nodes in the queue. Okay. And we will keep traversing as long as the queue is not empty. And also we keep track of a visited nodes list so that we don't go in a loop. So if we keep adding the neighbors and traversing, if we don't do the visited list, we will go in a loop. Okay. So instead, one modification we will do here is we have to also create the edges while traversing the graph, which is why instead of just a visited list, we will make this a visited map, okay, which has a reference from old node to new node. Let's say one is the old node and one prime is the new node. This map will contain something like this, okay. Anytime we visit a node, we will keep a reference of both old node and new node here. You will understand why we will need a map once we do the algorithm. So first let's write the simple BFS. What will we do? We will have a queue, and to the queue we add root. Okay, our queue will initially have root. Okay, while queue is not empty. Okay, while this is not empty, we remove a node from the queue. Okay, and for each neighbor, what do we do? If it is not visited, if not visited, add to queue, right? So this will help us traverse the graph. Now the change we have to do is at every point we have to create a new node, which means when you add the root element to the queue, what we have to do? We have to create root prime and add it to the map. Okay, our map is our visited list, correct? So we will add root prime to the map. Then if it is not visited, we are adding it to the queue, right? So here, if it is not visited, we will add instead of we while adding it to the queue, we also add it to the map. And if it is visited, whether it is visited or not, in both cases, we have to create a edge, which means we have to add edge from the current node into this neighbor. Okay, so the modifications we have to do are not just adding it to the queue. Every time we add it to the queue, we have to create a node and add the reference. And every time we traverse the neighbor, we have to add the edge. Then at the end of it, we will have a new graph. Now let's look at why we need a map instead of simple visited. So that is because of this additional operation we have to do. We have to add the edge as well, which means for each node, we need to know its new node as well. Correct? There is from the visited graph, we won't be able to find this new node, which is why we have to maintain the reference in a map and we have to add it. So when we write the code for this, it will be much more simpler actually. So let's look at the code. So initially, like they said in the problem statement, we are already given a class which has value and neighbors. Okay. So let's implement the function. Let's handle the case where node is or there is no graph. The graph is empty, which means node is null. If we handle these edge cases initially, our code would be cleaner. So now when we are at this point, that means there is a node, there is some graph. Okay. So for BFS, the first thing we need is we need a queue. Let's create a queue. Okay. Linked list implements queue. I am going to just use that. And we also need a map. Map is needed to track the visitors and also to get the reference of the new node when adding edges. Okay. So initially, what do we do? To the queue, we add the given node. Here the node is already not null. Okay. And we create a new root. Let's call it root 1 using this node. Okay. Once added, we also put this in the map. So the current root's reference is root 1. We added it to the map. Okay. Now the simple BFS traversal. While Q is yeah, Q is not empty. Sorry, is empty. While Q is not empty, we just remove a node from the queue. Okay, we are removing one element from the queue and we are getting all its neighbors. We have to traverse the graph, right? So in BFS, you traverse all the neighbors first. So let's get the neighbors. Okay, we are getting all the neighbors and let's also get the, for this node n, what is the node in the new graph? Okay, which would be n1. Okay, now for each neighbors in neighbors, so for each of the children, what do? We have, so there are two possibilities here. Either the neighbor is already visited, which means our map already has it, or the neighbor is not visited. Okay. So if the neighbor is not visited, okay, then we will not have its clone in the new graph. If the neighbor is visited, we will have its clone in the new graph. So let's call the clone of neighbor as neighbor 1. So if map dot contains key neighbor, that means this neighbor is already visited. In this case, neighbor 1 would be simply map dot get of neighbor. Okay. Else, if this is not visited, that means neighbor 1 we have to create a new one using the value of neighbor. And we also have to add it to the queue because this is not visited. We have to visit its children as well, which is why we have to add to the queue. In this case, we don't have to add to the queue because that is already visited. So this completes the is visited check. Now comes the point where we actually need have to add this edge. So we have this new node n1 here, which is a clone of the node which we are traversing. For that node and each neighbor, we have to add an edge. That means for n1 to neighbor 1, we have to add an edge, which means to the neighbors list of n1, neighbors is a list, right? We have to add the new cloned neighbor. Okay, right? And so yeah, here we also have to put this in the map because we have to mark it visited, right? Okay, so here we are creating the edge. So why are we creating the edge even for a visited node? Even for a visited node, sometimes the edge can be missing, which is why we have to do this outside this if else. Okay, so if it is already visited, just get the neighbor from the map. If it is not visited, create the new clone node, add it to the queue, put it in the map, and in both the cases, create this edge. Okay, at the end of it, we have our answer. We just have to return the new root 1 reference which we have created here, which would be in the map as a value of node. Okay, let's run this and see. Let's submit this. Okay, so this is our solution. So the thing you have to understand is you have to see why we need this map here instead of a simple visited node. Just do a dry run with the given example and you will understand it. Let us also do a dry run of the code with the given example. Okay. So what is the given example? The graph we were given were which had 4 nodes. Okay. So the graph was 1 which has neighbors 2 and 4, and 2 which had neighbors 3 and 1, 3 which has neighbors 2 and 4, and so on. And we were starting at 1. Okay. So let's do a dry run of this. So when we are at 1, see, clearly it is not equal to null, so it won't go here, it comes here. Now we create a empty queue. Okay. Let's say this is our queue, and in the next line we are creating a map. Let's say this is our map. Okay. What we are doing here, we are adding our current node to the queue, which would be 1. Okay. And we are creating a new node and putting its reference in the map. So here, let's call the new node as 1 prime. So we will have a reference of 1 and 1 prime here. So far this is our queue and map. Now what we are doing, we are removing the node from the queue. Okay, so which means the current node n would be 1. We removed it, so the queue is not there. And we are getting neighbors. Okay, we also got the n1 which is 1 prime. Okay, so n1 would be 1 prime. Okay, for each neighbor, what are we doing? So what are the neighbors in this case? 2 and 4 for each neighbor. That means we are at 2. What are we doing? We are checking if map contains 2. No, it doesn't contain. Then we are creating its new node which would be 2 prime, and we are adding it to the queue. Okay. Similarly, for n1s, so let's say we created n1 prime, right? We have this. So for n1 dot neighbors dot add neighbor 1, which means we are at 2, right? So we are adding 2 prime edge here. Okay. And for each neighbor, right? So we will process 4 next. So when we are at 4, again map doesn't contain 4, so we create a new node called 4 prime, and we have to add it to the map, which would be 4 is pointing to 4 prime, and we also add it to the queue. Okay. And we have to create this edge, which is 1, our current node 1 prime, basically 1 prime, and our current neighbor 4 prime. Okay, we create this edge. Okay, so far good. Now we continue this while loop. So our current n will become 2, n prime will become 2 prime, and our neighbors are 1 and 3. Okay, when we are at 1, 1 is already in the hash map. Okay, so we will just try to create an edge. That edge already exists. So that is fine. Okay, when we are at 3, that is not in the hash map. So the same process will repeat. We will create a new node 3 to 3 prime. Okay, we will add it to the queue, and for our current node is 2 prime, our current neighbor is 3 prime, we will add that edge. Okay, 2 is popped. Now when we take out 4, 4 again is already visited. So we just have to create the edges. Okay. What are the neighbors of 4? 1 and 3. Okay. So 1 is already there and the edge also exists. For 3, the edge doesn't exist, which is why we have to create this edge. So if you understand, here the edge was not existing, whereas the nodes were already there, which is why we have to do this edge creation outside this. That is the case which we are handling here. Okay. So now both of its neighbors are processed. There is nothing new to be added to the queue. Okay. Now the current node would be 3. Okay. And node in the new graph would be 3 prime. Neighbors of 3 are 2 and 4. Both of them are processed and both of them are visited and both the edges are also created. Okay. Finally, we just return map from the map reference of node, which would be 1 prime. Okay. So that's all. If you do a dry run like this, it will be very clear for you to understand the code. So thank you for watching. Please like, share, and subscribe.